All right, today we're going to be talking about 2.7 addition and subtraction theorems. Our learning targets are I can solve problems using addition and subtraction theorems. So let's go ahead and get started with a quick example. So with this problem, we're given PQ is perpendicular to QR. We want to find the measure of angle PQS, this angle right here. So to get started on this, and again, pause the video and try this one out because this is very similar to yesterday. This is our warm-up. First off, we see that PQ is perpendicular to QR, which means that they intersect at 90 degrees. This is a 90-degree angle right away. And also, that means that angle PQS and angle SQR, they're complements. They're complementary angles, meaning that they'll add to be 90 degrees. So I can set up an equation and say x squared plus 12 plus 43 minus 2x equals 90 degrees. Now, at this point, I'm going to go ahead and combine like terms on the left side of my equation and put it in standard form at the same time. So I now have x squared minus 2x plus 55 equals 90. Now, if I have x squared here, chances are I'm going to have to factor this thing. So I'm going to need to set the right side of this equation equal to 0. So I go ahead and I subtract 90 from both sides. And we're left with x squared minus 2x minus 35 equals 0. Now, at this point, we're going to go ahead and take our a value, and we're going to multiply it by our c value. Because again, these are written as ax squared plus bx plus c equals 0. So I multiply those two numbers and I get negative 35. Now I'm looking for numbers that will add to be negative 2 and multiply to be negative 35. And there's a lot fewer numbers that multiply to be negative 35. So I start listing them out. 1 and negative 35, negative 1 positive 35, 7 and negative 5, negative 7 positive 5. Out of all of these numbers, the only one that will add to be negative 2 is negative 7 and positive 5. So I create my double bubble, double parentheses down below, and the first thing that goes in the bubble is the variable that we're dealing with. And in this case, it's x. So I place an x first. The next thing that comes in the bubble are the two numbers that we found, negative 7 and positive 5. Now at this point, if it has its own parentheses, it gets its own equation. So I have x minus 7 equals 0, and I also have x plus 5 equals 0. So solving for both of these equations, we get x equals 7 and x equals negative 5. But we're not trying to solve for x, we're trying to solve for the measure of angle PQS. So we're trying to find this measurement here. So I just go ahead and I plug these numbers back in. If x equals negative 5, then the measure of angle PQS is equal to negative 5 squared plus 12. Well, that'll give me 25 plus 12, which is 37 degrees. If x is equal to 7, then the measure of angle PQS is equal to 7 squared plus 12. That'll give me 49 plus 12, which is 61 degrees. Now, looking at these two answers, we have 61 degrees and we have 37 degrees, depending on what value x is. So, is angle PQS larger or smaller than angle SQR? Well, looking at these two respective angles, angle PQS is larger. So if angle PQS is larger, that means that if the whole thing is 90 degrees, PQS needs to be larger than 45. It needs to be larger than half of that 90 degrees. So therefore, 37 degrees is out, and 61 degrees is the correct answer for the measure of angle PQS. All right, so let's go ahead and jump into our notes for today, and we're going to go ahead and start off with a conditional. So here's our opener. We have a whole segment here, segment AD. Now in that segment there's 2 points, B and C, that makes AB equal to 7 and CD equal to 7. What I'm wondering is segment AC equal to segment BD? Well, yes. Yes, they are. So I can go ahead and put yes to get started. So, as an example, we said that AB is 7 and CD is also 7. Now, we're looking for if I add BC to both of them, will they still be equal? Well, let's say that BC is an unknown length, it's x. Well, then I'm adding x to both of these. And we know 7 plus x is equal to 7 plus x. So therefore, these are true. This is a true statement. And this leads us to our first theorem, which is if a segment is added to two congruent segments, then the sums are congruent. Again, if a segment is added to two congruent segments, then the sums are congruent. So in this case, we have segment BC. So I'm adding segment BC to both segment AB and segment CD, because we can see that they're congruent based upon the tick marks. So if a segment BC is added to two congruent segments, when I say two congruent segments, I mean segment AB and segment CD, so we see that here, then the sums are congruent, meaning from A to C is congruent as B to D. So these two segments here, these are congruent to each other. Now, let's go ahead and prove this. So I'm going to set up a two-column proof real quick, and then you'll be able to see the paragraph proof on the next slide. So here's my statements. Here's my reasons. So to get started, my first statement is AB is congruent to CD. That's given. From here, if they're congruent to each other, then I should be able to say that they're equal. So AB is equal to CD. And that's by the definition of congruency. Meaning, if two segments are congruent, then they are equal to each other. And you'll see that in the paragraph proof. I have the conditional statement written out in that. From here, if that's the case, then I can say for number 3, AB plus BC is equal to BC plus CD. All I did here is I added BC to both sides, so that is our addition property of equality. Now at this point, if I combine these together, for number 4, I should have AC, that whole segment now, is equal to BD. So they're now equal, and all we did there is we added our segments, so that's the segment addition postulate. Segment addition postulate. Lastly, if two segments are equal to each other, then we should be able to say that they're congruent. So for number 5, AC is congruent to BD. And that's what we're trying to prove. The reason that we can say that is the definition of congruency. Again, that's the same thing as number 2. If two segments are equal, then they are congruent, by definition of congruency. Now, here is the paragraph proof of this. So again, use either one. So AB is congruent to CD. So AB is equal to CD because two segments are congruent, then they have the same measure. From there, AB plus BC equals BC plus CD by the addition property of equality. Therefore, AC is equal to BD by the segment addition postulate, which leads us to AC being congruent to BD because definition of congruency, meaning if two segments have the same measure, then they are congruent. All right, so that is our first theorem, and that's the only one I'm actually going to prove today. From here on out, the rest of these are just going to be showing you guys what these theorems are, but their setups are all pretty much the same. So our next one is if congruent segments are added to congruent segments, then the sums are congruent. Meaning, if I take my two red segments, because they're congruent, and I add them to my two green segments, because they are congruent as well, then the resulting segments, meaning the black segments here, those sums are congruent. Meaning if both of these are the same measure because they both have one congruency tick mark, and these are both the same measure because they both have two congruency tick marks, and I were to add them together, they should be congruent as well. And just as an example, let's say that these are equal to 6, the green pieces, red pieces are equal to 5. Well, what would the black pieces be equal to? Well, 11. And as we can see, they're equal in measurement, so they are congruent. So that's how we'll be going through these if needed. But again, this is just our second theorem. Now, that's all we have for segment addition. But you may be wondering, does this work for angles? And it absolutely does. So we can actually use these theorems for angles as well. So if an angle is added to two congruent angles, then the sums are congruent. So here, I'm adding an angle, and that's that red angle right in the middle here, angle JFH, right here. I'm adding that to two congruent angles, meaning the two blue angles, those 50-degree angles. Those are both congruent because they're the same measure. Well, then the sums are congruent as well. And when I say sums, I mean angle EFH, this green angle here, and also this other purple angle that I'll put right underneath. That purple angle is angle JFG. These two angles will be congruent to each other. So I can put 1, 2, 3, and 1, 2, 3. So those angles are congruent to each other as well. We have one last angle theorem as well, and it's just like our second segment theorem. So same type of idea, same concept. So for this one, if congruent angles are added to congruent angles, then the sums are also congruent. Meaning, I have these blue congruent angles here on either side. There's one here, there's one over, whoops, sorry about that, there's one over here. So we have those two blue angles, those are congruent. I'm adding them to the two red congruent angles. So if I add blue plus red, I'll get the entire purple angle. So those sums, those purple angles, will also be congruent as a result. So it's just adding these two segments together, or sorry, these two angles together to get the bigger angle. Now, those are all of our theorems for addition. Now we're going to move into subtraction. And I'm not going to have you guys write out all four once again. We're going to compress them together now. So they're the same exact theorems, except now we can subtract. So here's our first one. If a segment or angle is subtracted from congruent segments or angles, the differences are congruent. Meaning, here we have AC and BD, and they're congruent to each other. They both have two tick marks. If I were to subtract this middle segment, BC, from each of these, because BC is its own length, right? If I were to subtract BC from both of these, then we would have AB and CD, and those two angles would also be congruent. So, if a segment or angle is subtracted from congruent segments or angles, those are the black ones here, congruent segments or angles, then the differences are congruent. Meaning, AB, I only need one here, will be congruent to CD. So those segments are congruent. As for our final theorem, it looks just like our angle addition, except now we're using subtraction here. So, if congruent segments or angles are subtracted from congruent segments or angles, the differences are congruent. So let me go ahead and draw a quick example. I'm going to draw a triangle up here. It's going to look very similar to one that we just did a few minutes ago. So we have this triangle. Now, with this triangle, if congruent segments or angles are subtracted from congruent segments or angles. So let's start with this purple angle here, this full thing. We know that we have these two angles that are congruent. And I'm going to subtract this red angle from each of these. Well, will the resulting angle down here, will these be congruent? Absolutely. Absolutely. These blue angles will still be congruent. I don't need 3 of them, I only need 2. So those will be congruent as well. So, if congruent segments or angles are subtracted, meaning I'm taking these red angles here, and I'm subtracting them from the purple angles, from the other congruent angles I have, those purple ones, then the resulting angles are congruent, meaning the blue angles down here are congruent as a result. So if I take red from purple, I'm left with the blue, and the blues will be congruent. All right, lastly, let's go ahead and do an example problem. So given QR is congruent to ST. So let me go ahead and draw that. QR is congruent to ST. QS is equal to 5x plus 17. RT is equal to 10 minus 2x. And RS is equal to 3. We want to find QS and QT. So first off, I'm going to go ahead and set up some segment addition because I can see QR plus RS equals QS. So let's go ahead and do that. QR plus RS equals QS. And if I substitute in, I now have QR plus 3, QR plus 3 is equal to 5x plus 17. That's what this length was, 5x plus 17. And I just lost it again, so let me just post it up. So QR plus RS equals QS. QR plus 3 equals 5x plus 17. Now, from here, I want to solve for QR. So I subtract 3 from both sides, and I have QR is equal to 5x plus 14. And I'm just going to leave that here. Now, I see QR is congruent to ST, so I want to solve for ST as well. Now, if I go over to my other segment, RT, I can see that's equal to 10 minus 2x. RS is still 3. So I can say ST plus RS equals RT. So ST plus RS equals the entire thing RT. Substituting in my values, I now have ST plus 3 equals 10 minus 2x. And subtracting 3 from both sides, we get ST is equal to 7 minus 2x. Now, at this point, I know QR and ST are congruent, and congruent means that they're the same. So I can set them equal to each other now. So I now have ST equals QR, or 7 minus 2x equals 5x plus 14. Simplifying this down, we're left with 7x equals negative 7, so x is equal to negative 1. Now that I know what x is, I can find QS and QT. So to do this, I'm just going to find out what QR is equal to. So QR is 5x plus 14, so let me go ahead and plug in negative 1 there. QR is equal to 5 times negative 1 plus 14. Again, I'm using this equation right here. This will give me negative 5 plus 14, which is 9. So QR is equal to 9, which means that ST is also equal to 9. So therefore, I can say Q to S is 9 plus 3, or 12 units. And then for QT, QT is equal to 9 plus 3 plus 9. The whole thing. Q to R, R to S, S to T. That will give us 21 units. So our answer is 21 units for QT and 12 units for QS. And that is our answer. And also from here we can see that they are congruent. So QS and RT, those are congruent segments as well. All right, so that is it for today's notes. Again, our learning target today was I can solve problems using the addition and subtraction theorems. If you guys have any questions, please let me know. But thank you guys so much for watching, and I'll see you later. Take care.